Good morning, one and all. My name is Himanshu Kushwa, currently working as assistant professor in the Department of Electronics, Keshav Mahavidyalaya, University of Delhi. I'm also doing my research work under the supervision of Professor Jagneet Koranan, Department of Electronics, Keshav Mahavidyalaya, University of Delhi. So the topic of my presentation is performance optimization of surface plasmon resonance-based sensor from the first principle. So in this study, we basically optimize the surface plasmon resonance-based sensor due to the improvement in the optical coupling efficiency and investigated from the first principle. Various design parameters are optimized in a typical prism coupling configurations. So this is the these are the aim of study: performance parameter enhancement of SPR-based effectiveness sensors, and we also done the mathematical equation development for the electromagnetic field of the optical modes due to the plasma oscillations. And we also check for the gradient of electric field and its implication on the strength of the excitation of the plasmon modes in the SPR sensor, and input coupling enhancement with the increased transverse component of electric field. So this is the figure. This figure shows the typical SPR sensor in the Kretschmann configuration. Here NP, NM, ND, and the NA are the effective indices of prism, metal affinity layer, and the aqueous medium, the analyte bit containing the biomolecules to be sensed respectively. And incident light or the wavelength when fall with the wavelength lambda on the prism base at the input angle theta I. The SP modes are excited at metal affinity layer interface at the incident angle theta equal to theta, known as resonance angle. So from the figure, the mode of EX equal to E in sine theta I. Hence, to increase the EX, which is the transverse component of electric field, the value of theta I at which the SP mode gets excited should be large. So we define the input optical coupling efficiency as the percentage of the electric field intensity present in the input coupling electric field getting coupled into the SP mode, that is EX by EN equal to sine theta I. The real part of the effective index of the SP mode can be directly calculated from NP sine theta I product. So then we plot the electric field behavior. So these are the instant electric field lines appearing in the form of discontinuous loops are getting generated using the Maxwell equations for an SPR sensor configuration, which we have just shown you. The SiO2 is used as an affinity layer in the SPR sensor for the detection of bacteria like E. coli present in the aqueous solution. These figures shows the instant electric field lines appearing in the form of loops in the exact planes of the sensor at the gold silica interface. These figures gives the idea or the detailed view of the electric field lines over a propagation length of 1 micrometer. And the second figure shows the attenuation of the field lines due to the absorption at the metal affinity layer interface for a range of 40.6 micrometer up to the 40.6 micrometer. The field is completely absorbed after a distance of 40.6 micrometer, as we can see in this figure, which is the range of symmetric mode, TM0 mode, excited in the sensor. And we have calculated all this using the Mueller methods. Okay, so if a tangent drawn at any point gives a slope of the electric field that is Ex by Ez at that point, a large slope of the tangent at the metal direct interface signify that the electric field lines are predominantly transverse at the interface. Next, we similar plots of the electric field lines can be seen for all dielectric waveguides, and this is the configuration of symmetric three-layer planar all dielectric optical waveguide consisting of a high index dielectric core of thickness 0.6 micrometer, and we plotted the electric field lines for TM symmetric and antisymmetric mode, and the TE symmetric and antisymmetric field lines. So these are the electric and magnetic field line behavior for this. Next, we have seen that how we can increase our input optical enhancement, and that is due to the three factors: due to the change in the prism index, due to the change in the affinity layer index, and due to the change in the metal layer thickness. So by using all these, we optimize the various design parameter of SPR biosensor for enhancing the optical coupling efficiency. So these curve actually shows the for the enhancement due to the change in the prism index. So you can see the first figure shows the reflectivity curve versus incident angle theta I for various values of reflective index of the high index prism NP. With increase in NP, the resonance angle shift towards low values. You can see the height of the black arrow, which is in the first figure, gives a measure of the reflectivity dip. The inset figure shows the variation of the resonance angle versus NP. The second figure shows the plots of transverse and electric field intensities EX square and EZ square in the three regions, prism, gold, and affinity layer at 4 values of prism index. The continuity of the longitudinal component EZ square at the two metal dielectric interface can be seen from these plots, whereas the transverse component EX square does not show any continuity at the two interface. The third figure shows the plot of sensitivity, which is a blue line, and FOM orange line versus prism index for 1.4570, and wavelength is 632.8 nanometer. The sensitivity seemed to increase with the decreasing prism index, and FOM is not changing significantly. The inset figure of third figure shows the SNR and FWM variation, FWHM variation. Then we change the increase in see in the input optical coupling enhancement due to the change in the effort layer index, and plot all these three figures again. And similarly, we the input optical coupling enhancement due to the change in the metal layer thickness, and we again seen the variation of the reflectivity, electric field intensities, and sensitivity, FM, etc. Then we report the improvement of 6.8 degree per RIU, 0.6 degree per RIU, 7.5 degree per RIU, and 47.2 degree per RIU in the sensitivity, when the prism index actually vary from 1.65 to 1.62. Affinity layer index changed from 1.4570 to 1.4630. Gold thickness changed from 35 nanometer to 70 nanometer, and wavelength of input optical wave changed from 900 nanometer to 633 nanometer respectively. The corresponding enhancement in the input optical coupling efficiency is 64.33% per RIU, 58.787% per RIU, and 45.855% per micrometer, and 20.90 micrometer inverse respectively, which influence the real part of the effective index of the SP mode participating in the sensing application. The improvement in the sensitivity is the direct consequence of the increased real part of the effective index. With the increase in the thickness of the gold film, the real part of the effective index increases, whereas the imaginary part first reduce and then increase with a minima at around gold thickness of 45 nanometer, which is in the range of skin depth of the most of the metal at optical wavelength. The propagation length depends inversely on imaginary part, with the result that the propagation length of SP mode is maximum at gold thickness of 45 nanometer. That is why we have taken 45 nanometer gold thickness. So these are the conclusion part, that we have built mathematical equation development for the electromagnetic field of the optical modes due to the plasma oscillation. Then we check the gradient of the electric field and its implication on the strength of excitation of plasmon modes in the SPR sensor. Then we develop three methods of optical coupling enhancement due to the various physical parameter of DMD waveguide. And all this we have done for symmetric and antisymmetric optical modes of plasma oscillations and calculated their finite propagation length. These are the references. So thank you everyone for listening to me. I also want to thank the organizing team of NewSort 2022 for giving me this opportunity to present my research work in this event. Also, many congratulations to the organizing team for conducting such a wonderful and nice event. I would like to thank my supervisor, Professor Jagneet Kaur for her valuable guidance and support throughout this research work. Once again, thank you very much.